Greetings fellow YouTube viewers, it's time for another compendium video, and today I'm going to show you a really neat trick to finding that will help you find the line of intersection between two planes when the planes are given in Cartesian form. So normally to find the line of intersection in between these two planes, and if the line of intersection had to be given in vector form in particular, would be a very difficult task, but using my technique it's going to be very easy. So we see two planes. Let's just draw them on here. This is plane 1, and then this over here this is pi 2, and these two are intersecting. Now this diagram isn't very clear, so I'm going to show the planes as single lines that extend forever in this direction. So these are two planes, they're intersecting, obviously. Well, not obviously, but most planes intersect unless they're parallel or overlapping. If they're overlapping, they always intersect, but unless they're parallel, planes always intersect. Two planes always intersect each other, and so here we have a line of intersection. Let's call this L. So this is pi 1, this is pi 2. Now how do we find L? Well, L lies on pi 1, so obviously L is parallel to pi 1, and L is also parallel to pi 2. Now what we're going to use is a neat little property that if something is perpendicular to pi 1 and there's something that's perpendicular to that, then that thing that's perpendicular to the perpendicular is parallel to pi 1. So n1 is perpendicular to pi 1. Here we can see the vector n1. This is perpendicular to pi 1. So this angle over here is pi over 2, or 90 degrees. This angle here is also 90 degrees, or pi over 2. This is n2. Now n2 is perpendicular to pi 2. Now if L is parallel to pi 1 and pi 2, then L must also be perpendicular to n1 and n2, because again L lies on pi 1 and pi 2, so L must necessarily be perpendicular to both of these, and this is the defining property that we're going to use. So this implies that L is perpendicular to n1 and L is perpendicular to n2. Now the really cool thing is that we can see n1 and n2 easily from this. So we can say that n1, and we can see this just from looking at pi 1, that n1 equals 13 I plus 2j plus minus 9k, and I'm writing it in this visual form, which I prefer to the unit vector notation. And we know that n2 equals 5i minus 2j plus 3k. Now the direction vector of L, let's call it D. D is parallel to L, and let's just draw that on our diagram right here. D, right? And D is independent of any point. It's just a vector. Is parallel to L. So D is equal to, or let's just write KD. so that we can simplify. You'll see why later on. KD equals, and we're going to take the cross product of n1 and n2. So n1 cross n2. So we take the cross product of these two, and hence we're going to find D. So this is a lot of theory. Now let's come to the practice. So we saw these vectors, we saw these planes, we noted down the normals pretty easily. Would take 2 minutes max, 1 minute probably. And now we have to take the cross product. So KD, no, let's just write n1 cross n2. No need for the k. 3, 2 minus 9 crossed with 5 minus 2, 3. And I mean, you could do n2 cross n1. It would give you the same value. It would give you the same result in the end because it's the same line. But order does matter when you're doing a cross product. So I'm just going to go with n1 cross n2. So 2 times 3 is 6. Minus 9 times minus 2. So minus 18. 6 minus 18 is minus 12. 9 times 5. Again, the 5 comes down here. Minus 9 times 5 is minus 45. Minus 13 times 3 is minus 39. Minus 45 minus 39. 5 and 9 is 14. 4, 3 becomes a 4. 4 and 4 is 8. Minus 84. 13 times minus 2 is minus 26. Minus 2 times 5. So minus 36. And there's something you should be noting right now, and that's that we can simplify this a lot. So first of all of them are negative, but secondly, they're all multiples of 12. So this is 1, 12 7s are 84, 12 3s are 36. So this implies that D equals 1, 7, 3. Now, all that's left, so let's just write the general form for a line. So for a line, R, which is a vector, a position vector of a point on the line, R, the position vector of any point on the line, is equal to S, the stand, if you will, plus lambda times D, the direction vector. So we know D, lambda is just any number that's real. Now we need to find S. And to find S is actually quite a simple task. And there's basically an infinite number of values of S. But I'm going to show you a nice, neat little trick for finding a good value of S. So right now we have two equations with 3 variables. And as you know, except in very rare cases, it's impossible to solve these. They have infinite solutions. So in this case, they have infinite solutions as well. So what we're going to say is we know that at some point, Z is going to equal 0. At some point. And in most of the planes that you can come across, most of the lines, they're going to have a point where Z is equal to 0. There might be that tiny chance that it is not, but for the vast majority, only if it's parallel to the Z-axis and it has a Z value other than 0. Point being, most times you can use this trick. Otherwise, if Z equals 0 doesn't work, X equals 0 or Y equals 0 surely will. Okay, so you say Z equals 0, and then these two, this basically cancels out. So we know that we want to find S, right? Now S is the position vector when lambda is 0. So it's just any point on the line. We want to find any point on the line. And there's an infinite number of points on the line, and hence an infinite number of solutions for these two. But we just want to find any one point. So we say Z is 0. Okay? So then this becomes 13x plus 2y is equal to 17. And so let's call this equation number 1. And equation number 2 5x minus 2y is equal to 13. And these are very easy to solve, simultaneous equations. You add 1 and 2 and you get 18x is equal to 30. Then you divide and you can simplify. So this is 30 over 18. Both can be divided by 6, so this is 5 over 3. So if x equals 5 over 3, we know z equals 0, and then we can substitute this in for y. Now I could do it in 1, but I'm not going to because it's 13 and it's big. I'm just going to do it in 2 because the coefficient of x is small there. So 5 times x, which is 5 times x, which is 5 over 3, minus 2y is equal to 13. I didn't use brackets because I wanted to avoid confusion with these kind of bracket ones. So this is 25 over 3 minus 2y equals 13. Minus 2y equals, and this is 39 over 3 minus 25 over 3. And so this is 14 over 3. And hence y is equal to minus 7 over 3 because we divide by minus 2. You can also write 14 over minus 6, but I don't see why you would want to. Okay, so we know x, y, and z for 1 point. That's all we need. So hence s is equal to x is 5 over 3, y is minus 7 over 3, and z is 0. So we have a point. And if you want, you can substitute this in, and you'll see that it works. If you substitute these x, y, and z values, it works. So anyway, we have s and we have d. Lambda can be anything, so therefore we can write the equation of the line which we wanted, the line of intersection, r, which is the same as x I plus y j plus z k, but I'm not going to write that. I don't like the unit vector form. It's good for speaking, but aside from that, for writing I prefer the visual form. Okay, this plus lambda, and then we have the vector from here, d, 1, 7, 3. Now I actually made this question myself, and when I was making the question I just took a random point. I said 2, 0, 1, but in this case 2, 0, 1 is just 1 point. There's an infinite number of points, and because I said z equals 0 instead of y equals 0, I got 2, 0, 1. Now in this case, because I was the one designing the question, I obviously knew that I could use y equals 0, but when you're faced with a question that's unfamiliar, you don't know that. So I would just recommend, and this isn't wrong by the way, this is a less neat stand, less neat s vector, but it's not wrong. So, and you can prove that this also lies on the same line as 2, 0, 1 if you want, but I'm not going to over here. Anyway, point being, this is a very useful way in which you can find the line of intersection between two planes given in Cartesian form. All you have to do, if you have to find the vector equation of the line, all you have to do is you take the normals, you take the cross product of the normals, and notice something really brilliant that we did here. We said that this line is perpendicular to the two normals. So if there was a plane, a third plane, pi 3, and this is really the key thing that I want you guys to take away from this. This is a plane pi 3, and on pi 3 you have n1 and n2. You'll find that n3, the third normal, the normal to pi 3, is actually parallel to L, where L is the line of intersection. And that's really cool. I mean, you can get a kind of intuitive sense of it anyway. Like imagine a plane over here, these two lie on it, and this is perpendicular. But we can prove that as well over here, because this is perpendicular to this, so therefore this must perpendicular to this, and so on for n2 as well. And so let me go through the steps again. You take these two planes, you find the normals, which are obvious, the coefficients, right? And then you take the cross product of the coefficients, simplify if possible. And I worked very hard to make sure that this was simplifiable. It's actually really hard making questions. Massive respect for the examiners. Anyway, so usually in the kind of questions you get either the vector is going to be simple or you'll be able to simplify to make it quite simple. And then use z equals 0 to get x and y, or x equals 0 to get y and z, and so on. And simplify and use that in order to get a point. Remember that whatever value you set as 0 is the coordinate, so I didn't have to find z because I knew it was 0. Use that as the stand, the position vector of a point. And there, voila. Mademoiselles et messieurs, il y a l'équations line. Here it is. Alright. Namaskar, Shubhratri, goodbye.